Assalamualaikum, myself Sayyid Usama and my roll number is 21309. Here I am going to explain the adaptive filters. First of all, we are going to Wikipedia. According to Wikipedia, an adaptive filter is a system with a linear filter that has a transfer function controlled by variable parameters and a means to adjust those parameters according to an optimization algorithms. Because of the complexity of the optimization, almost all adaptive filters are digital filters. Adaptive filters are required for some applications because some parameters of the desired processing operations, for instance, the location of reflective surface in a reverberant space, are not known in advance or are changing. The closed-loop adaptive filter uses bandwidth in the form of an error signals to define its transfer function. Then we are going to PDF. After the Wikipedia, we are going to explain the adaptive filter according to the book point of view. And then here you can see the adaptive filters. First of all, definition of these adaptive filters are the adaptive filters are digital filters that automatically adjust their filters coefficients to adapt to the input signals using an adaptive algorithms. Then we are going to explain the application of these adaptive filters. First of all, the adaptive filters are used in telephones, echo cancellations, noise cancellations, channel equalizations, biomedical signals enhancement, and active noise controls and adaptive control systems. Then the purpose of these adaptive filters are suitable for environments where the signals characteristics change. There is spectral overlap between noise and signals, and noise is unknown or time varying. Then the limitations of the traditional filters. The traditional filters like notch filters with fixed coefficients fails to preserve the desired signal spectrum when there is strong interference with overlapping spectra. The adaptive filters advantages. The adaptive filters can effectively remove interference by adjusting to the signal environment. And then moving to the fundamentals of these adaptive filters. First of all, the types. The chapter focuses on adaptive FIR filters using the least mean squares, LMS algorithms, and recursive latest squares algorithms. Further reading for more advanced topics like adaptive infinite impulse response (IIR) filters with adaptive lattice filters refers to the text by Icons 2014, Strands and Hush, and Withdraw and Streams in 1985. The illustrative examples of the adaptive filters. First of all, we have noise canceller setup. Components consist of two analog to digital converters and a digital filters with an adaptive algorithms. Then, first microphone, in which we captures the desired speech with mixed with noise. And here you can see the equations of this noise cancel setups. Then we are moving to the second microphones, in which we captures only the noise which is fed to the adaptive filters. The assumptions of these adaptive filters. Here we are discussing two assumptions. First is uncorrelated over noise and then correlated by noise. Here you can see the noise in the first channel is uncorrelated to the desired signals. Then the noise in the second channel is correlated to the noise in the first channel. And then moving to the adaptive filters process. Goal: estimate and subtract the noise from the corrupted signals to obtain clean signals. And then adaptive algorithms. The LMS algorithm adjusts the filter options to minimize the error signals. And then LMS algorithms for one tap FIR filter option update. Here you can see the equations of this option update rule. Here we have a numerical examples in which we are doing the first initial step and then procedure, and then we are moving to result and observations. Convergence. The adaptive filter learns the noise characteristics after several adaptations and cancels the noise. Optimal coefficients. The adaptive coefficients converge close to the optimal value of 0.5. Enhanced signals. The process output closely resembles the original signals. And then we have a multiple types of these algorithms, and now we are moving towards the book. Here you can see the outline of this 9.1, in which we are introductions of the least mean square, adaptive filters, impulse, and now all this we are discussed in the PDF. Here we are all discussed. Then you can see the basic Wiener filter theory and adaptive algorithms, Wiener filter theory and linear predictions. Basic Wiener filter theory. Here you can see the Wiener filter again adjusts its weight to the produced filter output, which could be as close as possible to the noise contained in the co-corrupted signals. Hence, at the subtracted output, the noise is cancelled and the output contains the clean signals. Here you can see the figure of this basic Wiener filter theory. And here are the all the and now here is the examples of 9.1 in which we are going to optimal solutions of to achieve the minimal MSE and determine J minimum. Here are the examples of this in which our equations we are discussing here. Now moving towards the Wikipedia. The example of this application, the first example is the recording of the heat beat may be corrupted by noise from the AC means. The exact frequency of the power and its harmonics may vary from moment to moment. The one way to remove the noise is to filter the signals with a notch filter at the means frequency and its intensity, but this could excessively degrade the quality of each AC since the heat beat could also likely have frequency components in the rejected range. Here you can see the block diagram of this in which we have the idea behind a closed loop adaptive filter is that a variable filter is adjusted until the error, the difference between the adaptive input and desired signals is minimum. The least mean square filters and the recursive least square filter are types of adaptive filters. There are two input signals to the adaptive filters, which are sometimes called the primary input and the reference input respectively. Here you can see the block diagram of these adaptive filters in which here you can see the tap delay line FIR filters. If the value filter has tap delay the finite impulse response structures, then the impulse response is equal to the filter coefficients. The output of the filter is given by whereby k is referred to the light of the k time. Now steepest descent algorithms. As we pointed out, solving the binary solutions requires a lot of computation, including matrix inversion for a general multiple FIR types. The well-known textbook authors by Woodrow and Stevens describe the power of LMS algorithms by using the steepest descent algorithm to minimize the MSE samples by samples to locate the filter options. We first discussed the steepest descent algorithms using a single weight as illustrated by equation 2.9.27. Here you can see the examples of 9.5 where we are discussing in the quadratic MSE functions for the Venus filters. And here you can see these mean square algorithms. The application of the steepest descent algorithms still need an estimation of the derivative of the MSE functions that could include statistical calculation of a block of data. To change the algorithm to do the simple base processing, and LMS algorithms must be used. The develops to LMS algorithms in terms of sample based processing. We take the statistical expectations out of J and then take the derivative of to both are approximate by dj divided by derivative of J and then derivative of W. That is, here you can see the equations of this topic filters. Then recursive least square algorithms, RLS algorithms aim to minimize the sum of the squares of the difference between the desired signals and the filter output signals using the new samples of the filter output signal using the new samples of the incoming signal. The RLS algorithms compute filter coefficients in a recursive form at which iterations. Here you can see the derivations, and here you can see the applications like cancellation system modeling and line enhancement. Here we all discussed in the PDF. We are discussed in the PDF. Now that's all from my side. Thank you very much.